All right, so let's look at an example about how we're actually going to solve for the instantaneous rate of change using that equation that we found in the last video. So here's a problem. It's very similar to the problem that we had in the average rate of change video, but we've tweaked the wording a little bit and see if you can tell what wording is different. All right. So first of all, we're still asking, we got an equation for the position of an object right here, but now we are just asking for the velocity at a specific time. We're not asking for what the average velocity is between t equals 1 and t equals 4. We're asking for, hey, what is the velocity at that very moment? And from the last slide, conceptually, if we have t equals 1 right here, if we're looking for the instantaneous velocity, what we're looking for is the slope of this line tangent to that curve at that very point. Okay? Again, it's telling us instantaneously how is our position changing at that very moment. So if we're going to solve for this, see if you can use the knowledge from the last video to try to at least come up with a first step, maybe work your way through to solve for what that value will be. Pause the video and just give it a shot. All right, so if you've gone through and tried that, what you should see is that if we're going to apply that instantaneous rate of change equation, that's just going to be this. We are going to evaluate our position function at a t value of 1 plus h, and then subtract our position function using a t value of 1 into that, divide it all by our step size h, okay? So if you didn't get this far, pause the video again, and with this knowledge, try to rework the problem. All right, so if you've given it a shot, if you plug all this stuff in, what you'll see is this is what we've done right here. Basically right here, we have plugged in a value of 1 plus h in for t in this equation right here and right here. And likewise, we have plugged in a value of 1 for t in that equation. So therefore, this first parentheses is going to be s of 1 plus h. The second parentheses is s of 1. Now, really important thing right here. Notice that I have put parentheses around all of these terms. That is very, very important. Why do you think it might be important to include these parentheses in here? All right? Well, if you couldn't come up with a reason, I'll tell you it's because if you didn't include that parentheses, especially in the second function right in here, you might forget to distribute that negative sign, and then you would be in a world of pain because you would not be able to simplify this equation and it would not work. So be very liberal with your use of parentheses when you're solving these types of problems. They can, it's an easy way to avoid some very serious problems that you can get in your calculations. All right, so now when we have this, what are some things that you notice are going to happen? All right, so it immediately looks like this is really complicated. But try now, if you haven't gotten to this point, try simplifying this term by squaring that and just see what kind of stuff happens. Again, pause the video, try to work through this limit. All right? So if you've worked through the limit, it should simplify to something like this, okay? Right here, we've expanded that square term, we foiled it, okay? And then we've distributed negative signs where they need to be. What are some things you notice about this equation? There should be some simplifications that occur. All right, one of them that you'll see is, hey, we got a plus 1 and a minus 1, those cancel. We got a plus 1 and a minus 1, those cancel. We got a plus 2, distribute the negative sign, a minus 2 right here. So immediately this whole s of 1 term has disappeared. And we're just left with things with a bunch of h's, okay? So now, if we're going to go a little bit further, our limit will turn into something that looks like that, all right? So what do you notice about this? Okay, well, when you plug in h equals 0 into this limit, you're going to get 0 over 0, which is bad news, okay? However, there's a little trick we can do. What do we do when we get 0 over 0? Remember the previous subject of limits. We want to find what h value makes that 0 over 0 and remove it, okay? So what we notice is that in the top and the bottom, we can actually factor out an h. So if we factor out an h, what magic happens? Well, now we can cancel these two h's right here. And if we look at what it changes to, now we have the limit turns to this. Now if we plug in h equals 0 in that limit, we actually get a limit that exists. We don't get 0 over 0. We will actually just get a limit of, we will actually just get a limit of -1. Okay, So if we go back up to this, remember I told you the instantaneous rate of change is the slope of the tangent line to the curve. Doesn't it look like the slope of this line right here is -1 or close to -1? Well, that's what we just found. So this is an example of how you use that equation for instantaneous rate of change to find the instantaneous rate of change of a function at a particular point. In the next video, we'll discuss how we find the instantaneous rate of change at any point along a curve.